The covariance between two random variables tells us a little bit about how they're related. And if we modify the definition of covariance a little bit to get another quantity which we call correlation, that tells us more about how the two random variables are related. So let's recall what we know about covariance. If the covariance of two random variables is greater than 0, that means that when x increases or decreases, y tends to do the same. And the covariance of x and y is less than 0 means that when x increases or decreases, y tends to do the opposite. So having covariance be positive means something, having covariance be negative means something. On the other hand, if the covariance of x and y is 2 or 14 or 57, that doesn't mean much. Because these values are influenced by variance of x and variance of y and the relationship between x and y. So if we have a very large value, it doesn't mean that there's a very strong relationship. It could mean that one of these variances is very high. So to correct for the influences of variance of x and variance of y on the covariance, we can divide by them and get something that really just tells us about the relationship between x and y. So we define rho of x and y, which we call the correlation of x and y, to be the covariance of x and y divided by square root of variance of x times variance of y. And we can also write this as covariance of x over square root of variance of x with y square root of variance of y, because covariance of ax with by is just ab covariance of x and y. So whenever these random variables are multiplied by a constant, we can just pull out the constant. So if these are multiplied by 1 over root variance x and 1 over root variance y, then we can pull those out, and then that's how they get on the bottom of the fraction here. So now we've got a measurement of just the relationship between x and y that's not influenced by the variance of x and variance of y, because we're dividing by that. So now we can say a little more precisely about what the correlation of x and y is and how we're going to picture it. So correlation, rho of x and y, measures how close to a linear relationship there is between x and y. So to be specific, let me write this in a claim. If y equals ax plus b for some positive a, then the correlation between x and y is 1. If y equals ax plus b for a less than 0, then the correlation between x and y is negative 1. So to see this, let's write out correlation between x and we'll assume y is ax plus b for some numbers a and b. So by definition, this is the covariance of those two things divided by square root of the variances. So this is the covariance of x with ax plus b over square root of variance of x times variance of ax plus b. Now if we have covariance of x with this plus that, we can write this as a sum of two covariances. This is covariance of x with ax plus covariance of x with b. We split up the ax plus b because that's how covariance works. And then in the denominator we've got, so variance of number x plus number is, we can get rid of the additive part and pull out the constant. It becomes squared on the outside. So we have variance of x times a squared times variance of x. The b just disappears. Alright, so we have, now when we have covariance of something with a scalar multiple in there, we can pull the scalar multiple out. It doesn't become squared. So we've got a covariance of x with x plus covariance of x with b. Now to see what covariance of x with b is, let me write this out. So it's the expected value of x times b minus expected value of x, expected value of b. Now expected value is linear, so we can rewrite this as b expected value of x. Expected value of a constant is just that constant, so minus b expected value of x. So basically this part is 0. That's just going to go away. So what's left in the numerator is a times covariance of x with x over, alright, variance is a positive number, so square root of variance times variance is just variance. We can write that here. Square root of a squared is absolute value of a. Why am I not just writing a? Well, if we have negative 3 squared and take the square root of that, it's not negative 3, it's 3. It's the absolute value of negative 3. So when we take the square root of something and we don't know if it's positive or negative, we have to put absolute values here. Variance is always a positive number. So square root of variance squared is just variance. Covariance of x with itself, we said last time, is just variance. So we have a variance x over absolute value of a variance of x. Variance of x and variance of x cancel, and this is going to be either 1 or negative 1. If a is positive, it's going to be 1. And if A is negative, it's going to be negative 1. And that's precisely what the claim says. When A is positive, we get positive 1. When A is negative, we get negative 1. So when we have a value of correlation that's close to 1 or close to negative 1, that says that the relationship between x and y is close to this, or close to this. Now, an easy property of covariance is that if x and y are independent, then the covariance is 0. All right, and this is easy to prove knowing that that's true for the covariance. So, I don't know if I said this correctly. An easy property of the correlation is that if x and y are independent, then the correlation is 0. It's the same thing that happens with covariance, and it's because of how correlation is defined in terms of covariance. So, let's suppose x and y are independent. So then the correlation of x and y is the covariance of x and y over the square root of the variances. But when x and y are independent, the covariance is 0. So as long as the variances are positive, we don't want to be dividing by 0. Then x and y independent makes the correlation 0. Let me put this in the claim. Mm-hmm.